We went through the proof of this last time. So today we're going to look at the following corollary. So the corollary says let A and capital B be m cross n matrices over the field M, over the field F, sorry. Then the following two statements are equivalent. The first statement is saying that B is row equivalent to A. The second statement is saying that one can write B as P times A, where P is a product of M cross N elementary matrices. Here's the statement of it. So let's see how to prove this statement. So what we're going to do is we're going to start with the implication from the first statement to the second. So suppose that, and this is the easy direction, I think. So suppose that, can one of you please open it? I think they've come for it. And sorry for the bother. Thank you. Great. So we're going to assume that B is row equivalent to A, and then we're going to prove that this statement is true. So before we start, does anyone have any guesses on how you would prove something? Exactly. Anybody else wants to try after hearing this? Okay, so it's okay if you couldn't figure it out, but just like take a minute, think about it, and try to recall, right? Like so what was the definition here, right? So the definition of row equivalent was that you could apply a sequence of row operations, right? So you could apply a sequence of E1, E2, and so on, right? Ek on A to get B, right? That is sort of the definition of row equivalent, right? And then we argued that each one of these, right? So each one of these operations from the theorem we know can be written as some elementary matrix capital E1 acting on capital E and so on. Right? So okay, so let's see how to prove this. So some more explicitly. I think it's maybe I messed up the arrows. Okay, so here it's trying to argue the other way. So the first direction that it's trying to do is assuming that B equals P times capital A, and then P one can write as E1 times E2 and so on. This is just by definition because it's a multiplication of M cross N elementary matrices. And then we know that E1A is row equivalent to capital A, right? This is essentially what I was saying, like using the previous theorem. And E2 A1 times A is also equivalent to E1A, right, and so on. And therefore, you're able to conclude that the entire product is row. That's fine, right? It's completely straightforward. Yeah? Any questions? Okay. And the second direction is the following. So now we're saying that suppose that B is actually row equivalent to A, right? Now what we're going to do is we were supposed to apply elementary operations, and suppose that E1 to ES are the elementary matrices that correspond to the row operations that you needed to apply to carry A to B, right? So if you had to apply E1, E2, and so on up till ES, right, on A, right, in order to obtain B, then the corresponding elementary matrices, those we are calling capital E1, capital E2, and so on. And we know from the theorem that we just proved that EA is the same as E1 acting on. Right? Okay. So this is the statement, and so therefore the corollary works. Okay. Any questions? Is making sense? So let's continue then. So now we're going to look at invertible matrices, okay? And oh yeah, I have to also silence my phone. Just give me a second. Okay. Yeah, please take a moment and silence your devices if you haven't already. Great. So now what we're going to do is we're going to look at invertible matrices. And the point here is that, you know, we sort of already talked about inverses for fields, right? We spoke of, you know, if you have C, then there's a notion of C inverse such that when you multiply it, you get 1. Right? We already saw this for fields. One can ask, can something similar be said about matrices? And indeed, one can define such a notion, but one has to be a little bit careful, right? Because we know for fields, for example, C inverse is the same as C inverse C, right? And this is 1. But for matrices, this is not necessarily going to be the case, right? Because we saw that multiplication itself is not necessarily commutative. So we'll have to be a little bit more careful. So now the definition is of an inverse is as follows. So we're just going to keep track of this non-commutative part. So suppose that A is an n cross n square matrix over the field capital F. Okay? We say that an n cross n matrix capital B satisfying B times capital A is identity is going to be called the left inverse. Right? So if you multiply matrix B on the left and it gives you identity, it's the left inverse. You should do the same thing on the right and it gives you identity, it's called the right inverse. And if it so happens that the same matrix, regardless of whether it's multiplied on the left or on the right, gives you identity, then we call B a two-sided inverse and we say that A is invertible. Okay? So that's just sort of a nice way of saying that if it commutes, like if the inverse somehow commutes, then it's going to be we're going to call A. So it appears that we implicitly assume that the left and right inverses must be the same, right? So here, like one could imagine that maybe, you know, AB equals, say, CA equals identity, right? Here I put the same B, right, on both sides, but it could be that the left and right inverses are actually different, even though they exist. Okay? So it turns out that it doesn't matter, and we'll do like a quick proof. So here's the lemma. So the lemma says that suppose that you have A has a left inverse B and a right inverse capital C, then it must be the case that B and C are identical. They are the same. So how do we do this? So well, let's just apply the definition. Right? So we know that BA is identity and AC is identity just from the premise. And then we're going to say that, right, so we have B. We can write that as B times identity. Right? That is fine. There's no that's just from the definition of identity, right? So this step is fine. And now we know that so AC is identity, right? So we can substitute for identity with AC, and matrix multiplication is associative, right? So we can multiply BA instead of AC first, and then we know BA is identity already, and so therefore you get C equals B. Is that good? Okay. All right. So, so here's a remark. So if A has a left and a right inverse, then A is invertible and has a unique two-sided inverse. Right. So that's sort of a consequence of this fact, right? If you have a left and right inverse, it's going to be the same. Okay, and this is denoted by A inverse, and it's simply called the inverse of A. Okay. So we never proved that inverse was unique. Yeah, we didn't prove uniqueness here. Right? That's what I was also trying to check. I'll double check if there is a because I don't think the textbook gives any statement about. I don't know whether it's the definition that you would say that A inverse is the inverse of A when the inverse is unique, or whether one can have two different inverses. Yeah. So I'll check. Okay, this uniqueness I don't remember seeing a proof. This is tricky for me. Any more questions? Almost certainly is, but I don't have a proof, so I cannot claim it. So I have to check. There is a proof, okay, so I'll look it up next time and give it to you. I must have missed it. Okay. All right. So the story is the following. So it says that the following theorem is going to state some properties that we expect inverses to satisfy. Okay. So let's start with this theorem. So this theorem says that suppose A and B are n cross n matrices over some field capital F. Okay. Now, if A is invertible, it must be the case that A inverse is also invertible, and the inverse of A inverse is identical, is A itself. Okay. So this is like very reminiscent of how you would do it with scalars, right? Like, so we know that there's a scalar, you take the inverse of the inverse, and give you C. Right? So if C inverse exists, so if C is such that C inverse exists, right, then C inverse, the inverse of C inverse also exists, right, and equals C. So this sort of we already know for scalars, but it turns out to also hold for matrices. And the second statement it makes is that if both A and B are invertible, then the product is also invertible, and this is the inverse. Okay. So right. So okay. So let's just look at. So suppose that B is the inverse of capital A, right? And B times A is A times B is identity, right? That's just because we said when we simply say that there is an inverse of a matrix, it means that it's the unique left and right matrix, right? So you're going to have the same inverse act on both sides. And so now clearly A is also the inverse of B, right? Because what is the definition of the inverse of B? It is some matrix such that when you left multiply and right multiply, you get identity. So the definition is symmetric. Is that okay? Is it making sense? Okay. So finally, so that was the first step. The second one is we simply want to verify whether AB inverse is B inverse or A inverse. Sorry, B inverse times A inverse, right? So this we can just do by a direct calculation. So you multiply and you're going to see that from the associativity of multiplication, you can get the answers. It's very straightforward things, nothing very complicated. Everything okay so far? Yeah? Okay. Okay. Now, here's the final corollary. So a product of invertible matrices is invertible. Okay. So this is sort of just generalizing what we said about, right? So if you have a product of these matrices and you take this as the inverse, it's easy to check that it will give you identity. So there's nothing going to happen. Well, so now let's look at theorem 11. It says that an elementary matrix is invertible. Okay. So let's say that capital E is an elementary matrix corresponding to some row operation little e. Okay? And suppose that little e sub 1 is the inverse of little e. Okay, so recall that in theorem 2 we said that for every elementary operation, right, we can find an inverse of the same type. So let's denote by e sub 1 the inverse of e. Okay, and let's call capital E1 little e1 acting on identity. Okay? Which is also how we define capital E, right? This is literally acting on identity. Okay, so then we're going to observe that the following holds. So capital E times capital E1 is the same as little e acting on capital E1, right? Is that okay? Right, because we proved that capital E times A is the same as E times A, right? This was like one of the statements here. Okay, so this is the case. And then we can apply the same argument here, not the same argument, sorry, the definition of E1, so you can substitute that. And then we know that E1 is the inverse of E, right? And we also saw that these you can, the order doesn't matter, you can do it in whichever order, so you will get identity. Is that okay? Does it make sense? Okay. All right. And then one can also run the same argument but backwards, and you would get again the same result, which means that E is invertible and E inverse happens to be E1. Very straightforward. Okay. So now let's look at some examples. Okay. So this matrix, right? The inverse of this matrix is itself, essentially. So this is, yeah, you can just check this by direct computations. I'll probably leave this as homework assignments to check. Just multiply it out and you will see what it is. This one looks a little bit more non-trivial. The only thing that changes is that you put a minus c here, and why that's happening is sort of also clear because you do row times column. So 1 c 0 1, 1 0 minus c 1. So let's go through one example at least, right? So it would be good. So okay. So what is the answer? Tell me. So what is the first entry? Yeah, but expand it out, right? We're babies, so 1 plus. Okay, so c times 0. So that's the first entry. What is the next entry? Wait, what? What did I do? Did I do it wrong? Ah, no, I forgot the c. Right. Okay. No. Oh yeah, it's fine. We want it to be identity. Okay, good. Yeah. And then the next one. Right. And the final one. Right. So is that good? Just a quick example to sort of get some handle on how these things work. Okay, this one is completely trivial, right? You just have the inverse and here also. So, okay, good. Right. So now we have the next theorem. So this theorem is saying that if A is an n cross n matrix, then the following statements are equivalent. So the first statement is that A is an invertible matrix. A is row equivalent. Sorry, A is row equivalent to the n cross n identity matrix. Right. And A is a product of elementary matrices. So these three statements are equivalent. So let's see how we can show them. You can take a minute to think about it if you want. Okay. So right. So let's set up some notation. So let R be the row reduced echelon matrix equivalent to A. Right. And in theorem 5 we showed that such an R always exists. Right? For every matrix one can do this. The next step is E1 to Ek are elementary matrices such that one multiplies capital A with these elementary matrices to obtain capital R. This we already proved, right? We just proved like a theorem 9. Okay. Okay. And yeah, I've actually written out the theorem. So this was theorem 9 that we just proved in theorem 5. So theorem 5 said that every matrix has a row equivalent row echelon form, right? Sorry, row reduced row echelon form. Yeah, sometimes I think somebody had asked actually on emails, or sometimes they say row echelon form because I tend to get a bit lazy, but yeah, the correct word is row reduced echelon. Okay. And theorem 9 is just saying that one can always do this. That if you have an elementary operation, you can replace it with elementary matrix multiplied with capital. Right. So now note that. Okay. So now note that E sub I are elementary matrices and they are invertible, and so therefore capital A can be written as follows. Okay. So we just proved that elementary matrices are invertible, right? And a moment ago we just gave a proof of that fact. So now we can just multiply by their inverses to obtain this object. Is this okay? Yeah, it's relatively straightforward. Okay, so now we're going to have three claims, and then we'll use these three claims to essentially establish the equivalence of the three statements that we have. Right? So these were the three statements. That A is invertible, A is row reduced to the identity, row equivalent to identity, and A is a product of elementary matrices. So we'll show that these three are equivalent. So the first thing we do is we look at the following. So A is invertible is equivalent to R is invertible. A is invertible is equivalent to R is invertible. And why is that? Well, because the product of invertible matrices is invertible. Right? So whatever you were using to argue is the inverse, you can use the other one to produce the inverse. Is that okay? So for example, if you had, if A times M was identity, right? Then we know that, this, so A can be substituted with some sequence of E's. So it's E1 to say EK, E1 times A, right? Oh no, I wanted the inverse. Okay, so E1 inverse all the way to EK inverse times capital R, right? This is just that statement. So this multiplied by capital M is identity, right? And this entire matrix now we can call the inverse of capital R, because product of invertible matrices is invertible. So it's fine. Okay. So we've explicitly established the inverse, so this is fine. Now the next one is if capital R is invertible, then this is equivalent to capital R being identity. Okay, so let's do that. So it says since capital R is a square row reduced echelon matrix, right? R being invertible is essentially equivalent to the fact that each row of capital R contains a non-zero entry. Right? So what do we have here? We are basically saying that so capital R is a square row reduced echelon matrix, correct? So a square row reduced echelon matrix, it cannot have so basically the first entry always has to be 1, right? And if it has any 0 rows, then obviously it cannot be inverted, right? Because if you have zeros, you can never multiply it with anything to give you an identity. So it must be the case that there are no non-zero rows. There are no non-zero rows. Oh, sorry, no all 0 rows, what am I saying? Right? So that cannot happen. And you have, it's a square matrix, right? So if these n rows have to be non-zero and you have n columns, then you have to have a diagonal matrix, right? There's nothing else you can do. Right? Just from the definition of row echelon. Okay. So therefore, if R is invertible, it must be that R is identity. Is that okay? All right. And the third claim is the following: that if R is identity, it implies that capital A is exactly this matrix. Okay. And this essentially just follows from this identity we had earlier, right? So if we know that capital R is identity, right, then A is just whatever else is left. Yeah? Is it making sense? Let me know, okay, if something is not clear or if you're getting left behind. Yes? Okay, okay. All right. Okay, so, and then now what we're going to do is we're going to use claim 1 and claim 2, right, to conclude that statement 1 and statement 2 are equivalent. So statement 1 was, statement 1 was A is invertible. And statement 2 was that A is row equivalent to identity, right? So from 1 and 2, we basically get that these two statements are equivalent. Okay. And claims 2 and 3, they are showing that statement 2 implies statement 3. So the fact that A is row equivalent to identity implies statement 3, which is that A is a product of elementary matrices. Right? This is just this statement here. Is that okay? So say it again. If, wait, I'll write it down. Okay, so if A
is an A cross N matrix, then we have to prove the following three points. Wasn't that the proof?
Then prove, yeah, 1 is equivalent to 2 is equivalent to 3, yes. So what that, so you, okay, this the statement is the following. Okay, so I think, yeah, maybe it's good to clarify this. Got it, right? So this is like the premise, right? So this is, what you know. So the important thing is it's a square matrix. If the matrix is not square, then all bets are off. We don't know what's happening. So we are assuming that it's a square matrix, and then we are saying if it were the case that 1 is true, then it would imply 2 is true. Okay? And the other way. If 2 is true, then 1 is also true. And so on. Okay, so that is what we do. Okay. Any more questions?
How many Theorem formally that if a matrix is invertible, then it cannot have
Um, it's just a linear combination. It's just from the definition of matrix multiplication, right? Because if you have one, the last row is entirely zero, right? Then the last column will always be equally zero, so you can never have identity. Yeah, yeah. So for example, if you have, so suppose this is say R1, R2. So this is say Rn, okay, and suppose, so these are rows, okay. So each of these are rows, right? And say you're multiplying it with C1, C2, Cn, right? Would ask the question. Oh, okay. You could read. Okay. So now the point is that Rn times Cn has to be this matrix, right? Sorry, it has to be 1, right? Because we want the last entry here to be, so we want this result to be identity, right? So we want this to be 1, 1, 1, right? So it means that this has to be true, but if Rn is identically 0, there's nothing you can put for Cn that will be true. So they cannot exist in it. Huh? It takes 2 minutes, you can prove it in the exam. But you can state it, it's fairly straight. Okay, I don't really know how they would grade it, so you should check with the TAs for grading and things. But yeah, it's not difficult to show. Any more questions? Yeah, so here the question was, yeah, maybe I should write. So the question was, if R is invertible, so R was like a row reduced echelon. Then, so if R is invertible, then R cannot have all zero, any all zero. Right? That was the question, and this is the proof. Anything else? Wait, let me write it down. So question: A is an n cross n matrix. No. So okay, so we have to be a little bit more careful. So the statement was, okay. So let me write down the question. The question was, A is an n cross n matrix, and because we proved the theorem, it implies A cannot have non-zero rows. Sorry, cannot have all zero rows. Right. No, your intuition is correct. It's just a question of how you formalize things. Okay. So that was also the question that was asked by your colleague here. Okay. So the point is that we are just saying that this is the premise. Okay. So maybe one way of saying is that if A is yeah, like I don't know. I think it's maybe much easier to give you a slightly different example. So suppose that A is a cat, okay, and the statement is that if A is a dog, okay, then A is a cat. Oh, sorry, A is a dog. A is an animal. All right. So this statement is true, right? But it's just that the premise is not like, it doesn't imply that A has to be a dog, is what I'm saying. So the statement is, so this is your premise. You're given that A belongs to some set, there's some elements, okay? So if there's like the set of animals, so there's like cats, there's dogs, there's whatever. So these are animals. And the premise is that A is like one of these objects, okay? That's fine. And the claim is that if A satisfies some property, namely A being a dog, then A satisfies another property, meaning A is an animal. Okay? But this statement does not say anything about what A has to be. It only says that if A was satisfying some property, then A would also satisfy some other property. So in that sense, you could have an n cross n matrix with 0 rows, with multiple rows that are 0, but then none of the statements would apply. All it's saying is that the conditions that the statements are talking about, they're equivalent. So instead of checking whether the matrix is identity or not, you could check whether you can write it as a product of elementary matrices and so on. The statements that we made here apply to, so these are basically a bunch of different criteria, and the criteria are equivalent, that is all. So if you want to check whether or not A is invertible, you could directly check whether it's invertible, or you could check whether the matrix can be expressed as a product of invertible matrices. Okay, so it has no bearing on what A has to be. It is just saying that the criteria are equivalent. Is that point clear? Okay, I mean this is going to be formal math, so it's sort of good to clarify these things. All good? Okay. So let us continue then. All right. So what we've done is we've said 1 is equivalent to 2. We've said, 1 is equivalent to 2. Okay, and we said 2 implies 3. So we said 1 and 2 are equivalent, and we have said 2 implies 3. Okay, it remains to establish that 3 implies 2 as well. Okay, and statement 3 is saying that it's a product of elementary matrices. Okay, and we want to say that if it is a product of elementary matrices, it must be the case that A is row echelon equivalent to identity. Okay, so let's see how this happens. It happens because elementary matrices are invertible, right? So one can construct inverses of A explicitly to show that A is row equivalent to identity. Right? So what this is saying is that A was basically this, right? It was like En whatever, sorry, Es to E1, right? It was a product of elementary matrices, right? And we know elementary matrices are invertible, so you can explicitly just multiply it S inverse whatever, E1 inverse A, and this will give you identity, right? Because we know elementary matrices can be invertible, right? This we already established. And so this has to be identity, and then this is basically just saying that A is row equivalent to identity, row reduced echelon, or just say row equivalent to identity. Is that okay? So you just have to be careful with the implications. Okay, these things are relatively straightforward, but you just have to make sure that you know what you're doing and from which direction. Okay. All right. So. Okay, so let's move on. Right, so the corollary here is the following. So if A is an invertible n cross n matrix, okay, and if a sequence of row operations reduces A to identity, then the same sequence of operations, when applied to identity, gives you A inverse. Okay. So this I'm going to leave as a homework exercise. All that this is saying is that if you have A and you multiply it by a sequence of operations, elementary operations that gives you identity, then it is claiming that if you apply the same sequence on identity, then you basically get A inverse. Okay, that's it. So leave it as it's like one step. Okay. All right. So oops. So let's look at the corollary next. The corollary here is saying, sorry, just give me a second. Some of the internet is a little bit unstable here, so I'm trying to see if I can join. Okay. Great. So let's continue now. So here what we are saying is that let A and B be m cross n matrices. Okay. Then the claim is that B is row equivalent to A is the same as saying that B can be written as P times A, where P is an invertible m cross n matrix. Okay, so I wrote down the proof very quickly. So one direction is straightforward. Right? So it says that one can write capital B as so if one can do this, right? So if one can write capital B as some sequence of row equivalent, elementary row operations acting on capital A, then clearly one can write B as a product of these elementary matrices, and these are invertible M cross M matrices. So this part is fine, right? So this is basically what P is, right? In that case, so that part is trivial. The other way. The other direction is saying that if you can write B as P times A, right, where this is invertible, then we want to argue that B is row equivalent, right? So B is row equivalent to A. But what did theorem 12 tell us? So theorem 12 said exactly this, right? So it said that instead of showing that so okay, what did I do? So okay, so it says use theorem 12 on point 1 and point 3 and apply it to P. Okay, so if P is an invertible matrix, it's a product of elementary matrices, and we know that if so here instead of A we're going to think of P, okay, and if P is invertible, then we know that it is row equivalent to the identity matrix, correct? Okay, so what that means is that P is going to be a product of so let's say E1 to En, right, acting on A, because we know that in an invertible matrix is just a product of invertible matrices, and invertible matrices is a product of elementary matrices, right? So here what we are saying is that this P, because it is invertible, it has to be a product of elementary matrices, and so therefore we can write B equals a sequence of elementary matrices multiplied with A, right? And this in turn basically just means that there exist operations, right, elementary operations that would carry A to B, right, which is what we wanted to prove, that B is row equivalent to A. Is that right? Okay, so this is basically telling you that it's nice to have this characterization of invertible matrices. So from the fact that P is invertible, we know that P can be written as a product of elementary matrices, and then that allows us to show that two matrices are row equivalent. Is that right? Well, any questions? Okay. So let's now look at theorem 13. So theorem 13 is saying the following. So for an n cross n matrix capital A, the following three statements are equivalent. So okay, so here it says that A is invertible. Okay. The second statement is saying that the homogeneous, I don't know what else, I'm a bit tired when I was reading. So the homogeneous system Ax equal to 0 has only the trivial solution, x equal to 0. Okay. So that's the second equation, the second condition. And the third one is that the system of equations Ax equals y has a solution capital X for each n cross 1, basically the column matrix y. Okay, so these are the three statements. Is the theorem statement clear? Yeah. So here what we are doing is, so we are given that, right, so we are given that B equals P times A, right? And we are given that P is an invertible matrix, correct? Just from the statement itself. And if you remember, theorem 12 was basically saying that being invertible, right, is equivalent to saying that the matrix is a product of elementary matrices. Product of. Okay. So if you apply that statement here to P, then it means that one can write P as some sequence of elementary matrices, right, acting on capital A, right, and this entire thing has to be B, right? I mean, that's what this is, right? And so then, and after that, it's clear, right? Because every elementary matrix you can think of as an elementary operation, and so that means B. Is that good? All right. So okay, so theorem 13 is the statement clear? So A is invertible, so that's one. The homogeneous system Ax equal to 0 has only the x equal to 0 solution as it only has the trivial solution that x has to be 0. And the third part is that the third statement is that the system of equations are non-homogeneous equation now. So Ax equals y has a solution x for each of the y's. So let's see how we would prove something like this. So first of all, we note that according to Theorem 7, I forgot what Theorem 7 was. Let's see. We have a set of statements. Theorem 7. Okay, so Theorem 7, recall, is saying that A is rho equivalent to the n cross n matrix if and only if Ax equal to 0 has only the trivial solution. Okay, so this we proved a while back. So if A is rho equivalent to the n cross n identity matrix, then Ax equal to 0 will have only the trivial solution. Okay, so rho equivalent to identity is the same as Ax equal to 0, the only solution. 0 has x equal to 0 as the only solution. Is that okay? Alright. It's according to Theorem 7, condition 2 is equivalent to the fact that A is rho equivalent to the identity matrix. Right? So this condition itself is just saying that it has to be, the matrix has to be rho equivalent to the identity matrix. Right? Okay? And NP2 is saying that from Theorem 12 and the statement above, it follows that 1 and 2 are equivalent. Right? Because, so Theorem 12 said what? So Theorem 12 said that invertible, right, is equivalent to rho equivalent to identity. Right? That was like one of the steps of Theorem 12. And we just said that being rho equivalent to identity from Theorem 7 was that Ax equal to 0 has x equal to 0 as the only solution. Right? So this is fine. Now what is the approach? Now we're going to look at 1 is equivalent to 3. Okay, so we already established 1 and 2 are the same. Now we want to show that 1 and 3 are equivalent. Okay, so this step is done. Now this is the one that we'll focus on. So, right, so let's start. So if A is invertible, right, then x equals A inverse y is the solution. Right, so that is obviously fine. If you have an invertible matrix and you have Ax equals y, you can just write x equals A inverse y, and that would immediately give you a solution for x. So this is okay. So that basically means that 1 implies 3. Right, so what is 3? 3 is saying that regardless of what y I have, I can find an x that satisfies the requirement. Okay, so we've done it explicitly. We've just immediately given you the x that gives you, that solves the equation. Now what we want to do is the other way, right? So we want to show that if it is the case that you can always find a solution, right? So you can always find an x. So this is saying if always there exists x solving Ax equals y, then it must be the case that A is invertible. Right? So let's try to see how we would show this. Okay, so what we do is we are going to show that point 3 implies that A is rho equivalent to the identity matrix. Okay, that's what I just said. And the way we do it is we start with looking at Ax equals y. Okay, and the premise just says that, not the premise, the statement just says that it has a solution for every y. Okay, so let capital R be the row reduced echelon matrix, which is equivalent to capital A. Okay, so that's just the nomenclature. So R is row reduced echelon for A. Okay, and what we want to show is that R is going to be identity. Right? Okay. So how we're going to do this is the following. Yeah, okay, maybe I missed one step here. So instead of showing that A is invertible, we're going to focus on the fact that R is identity, right? Because if you have an invertible matrix, it's going to be rho equivalent to an identity matrix. Right? So that's what we're trying to do here. So we are saying that suppose that A satisfies this equation, that there exists a solution to this equation for all y's, then we'll show that A is rho equivalent to R, where R happens to be identity. Okay, so how do we do this? So showing that a row reduced echelon matrix capital R is identity is the same as showing that the last row of capital R is not all zeros. Right? This is the statement that you were asking. Right? So this we can prove. So now what we do is since we are at liberty of choosing whichever y we like, we choose y to be this specific matrix capital E, which has all zeros except for the last entry. So maybe I should add a 0 here, and then the last entry is 1. So now, because we know that Ax equals y has a solution for every y, right? What that means is that Rx would be equal to E, can be solved for x. Okay, so let me rephrase it. Suppose that Rx equals E can be solved for all x's. Okay, then the last row of capital R cannot be 0. Is that obvious? Is it clear? No. Okay, so let's take a look, right? So suppose that you had the last row was all zeros. Okay, so it's very similar to the proof I gave earlier, right? So it's R1, these are all the rows. Okay, and suppose that Rn was like 0, like it's a 0 row. Okay, so it's a 0 row, all 0 row, all 0. Okay, so this is the case, and you have to multiply it with some x, right? X1 to whatever, xn. Okay, let's assume it's a square matrix. Okay, for now, I think it is in the premise everything is square, right? Or not? Yeah, it's a square matrix. Okay. So let's there is some x, right? And you want this to be equal to all zeros except 1 in the last entry. Correct? So now when you do matrix multiplication, what you're going to get? You're going to get okay. So this x I'm just going to call x as like the entire column. Okay, so let me remove this and just call it x. It's like this. The entire column is being denoted by x. Right? So now Rn dot x has to be 1, right? That's what we want. That's the constraint. But Rn is identically 0, right? So this can never be satisfied. So because regardless of what value of x you give, it will multiply with zeros and it will give you 0. There's no way sum of zeros can become 1. Okay, so cannot be satisfied. And so therefore, it must be the case that if there is a solution, then the last row cannot be all zeros. Right? Okay. So that is what we said here. So if this system can be solved for x, then the last row of R cannot be 0. That's all we say. Okay. All right. And we already know that the set of solutions that you're going to get for row equivalent matrices is the same. Right? So whether I'm trying to find solutions for A or I'm trying to find solutions for R, the solution set is going to be identical. Right? This we showed very early on. So now, what does it say? It says that Rx equals E can be solved for capital X. Wait, what did I do? Wait. Right. So what we have established now is that if it is the case that Ax equals y holds for all, like you can solve it for all y's, right? Then it must be the case that you can also solve Rx equal to E for all e's, right? Because the solution set is the same, right? So far so good. In particular, what that meant is that R cannot have a zero, all zero row. Right? So far we sort of established. And now what we want to show is that if R has no non-zero rows, right? Because wherever it had a zero row, you could have chosen E accordingly. Right? Like I said, the last row cannot be zero. You can put one wherever you want, and you can argue that no row can be identically zero. And now what we want to argue is that if there is no row that is identically zero, then you can always find a solution. Right? So that is what this last step is doing. It's saying that Rx equals E can be solved for all x. You know, given we showed that R cannot have any all zero rows. Okay, and all right. So then R equals PA. This we already know, right? Because R is now essentially the identity matrix, right? Good. Yeah, R is the row reduced echelon form, and it has no non-zero entries, so therefore R is just the identity matrix. And we know that using the corollary that we had above, which was basically saying that if you have an invertible matrix, then you can write it as, right? So if B is row equivalent to A, then B can be written as a bunch of a sequence of invertible matrices. Sorry, an invertible matrix times A. So here what we are saying is that we know that R can be written as P times capital A. Oh no, I think I gave you the wrong corollary. Okay, so we had that P was an elementary matrix, right? Product of elementary matrices, and we showed that product of elementary matrices are invertible. Okay, so this we already know. Sorry, I messed up the argument. Okay. So we know that because A and R are row equivalent, so one can write R equals P times A, where P is just a bunch of elementary matrices. And because they're elementary matrices, we already showed that they can be inverted, right? This we established. Right? So therefore one can write Rx equals E is essentially equivalent to saying PAX equals E, right? Because I have just substituted for R from this equation, so I can write PA instead of R. And then I can write AX equals P inverse of E, right? Because P was invertible, I can do this. Okay, so what does that tell us? It tells us that we're basically able to find solutions for AX. Oh, sorry. Since we assumed that 3 holds, so 3 was, yeah, so since we know that AX equals Y has a solution, right, that was the premise. So we know that regardless of what you put here, it will have a solution, and this having a solution is equivalent to the first system having a solution, right, because they're all equivalent. Okay, so if there was an X that was satisfying this, it must equivalently also satisfy the first system. So it's kind of a long argument, but you can go back and look at it, and it should sort of check out. Any confusion? Okay, so let's move on. Right. Okay, so the next statement is a corollary, right? So it's saying that a square matrix with either a left or a right inverse is invertible. So let's look at this. So suppose A is an n cross n matrix, and suppose that A has a left inverse B such that B times capital A gives you identity. Right? So that's what it means to have either a left or right inverse. And now we know that AX equal to 0 has only the trivial solution, right? Because, so let's work it out. So x1 can write as identity times x, this is fine. And identity we can write as B times A, right, because of this over here. And B times A, well, so now one can use associativity, and you can multiply AX and get this. Another point is that this will only have the trivial solution, because suppose there were a non-zero solution, okay, such that AX equal to 0. Okay, so if suppose for contradiction that ax there was a non-zero x such that ax equal to 0, then on the left hand side you would have x which is non-zero, and then on the right hand side you would have something which is 0, right? And that would give you a contradiction. Is that okay? No. Okay. So let me say it again. So here we got to the point we started with x, right? We said we can multiply x with identity, nothing changes. Okay, and identity we can replace with b times a dot x, right? Because b times a we are assuming is the left inverse away, right? Now b times a, so we can now recompose it, right? We can write it as a times x. This is fine. And from this we are concluding. So the conclusion now is that ax equal to 0 not possible unless x equal to 0. Okay. And the reason is sort of similar, right? Like you can just think of like regular algebra, right? Like so if you have x equal to like little a times x, right? The only way you can satisfy is if x is 0, right? So it's a very similar argument. Here what it's saying is that suppose that it were the case. So suppose that x is not equal to 0 and ax equal to 0. Okay. So then it would mean that x which equals bax, right? This quantity is 0, but this we just said is not 0. That cannot happen. So that's all it was saying, that if it is the case, yeah, sorry. So we were just trying to argue that ax equal to 0, this equation has to have only the only possible solution is the trivial solution. That is what we were trying to argue. If it has a left inverse. Okay. Okay. All right. And now using theorem 13, it follows that A is invertible. Okay. And theorem 13 was saying what? I forgot already. This is annoying. So theorem 13, let's see. Right. So theorem 13 was saying that these two statements are equivalent. Right. So the whether A is invertible or not is equivalent to checking whether ax equal to 0 has any non-trivial solutions. Right. And we just proved that the only solution is the trivial solution. Correct. And so therefore we get that A has to be invertible. Right. So let's do that once more. So what we're trying to do now is we are saying that so suppose that the following things are true. So the first thing that's true is that b times a is identity. Okay? And the second thing we're going to assume is that ax equal to 0 has a non-trivial solution. Okay, and we'll show that these are so this will contradict. Okay, so that's the strategy we're going to follow. And how do you show this? Well, you start with the following, right? So you start with x. You just write x, and x we can write as identity times x, right? So this is completely fine. Identity times x, because we assume this statement, right? So using one can write ba times x, right? The substitution. So far so good. And now one can do associative. So because matrix multiplication is associative, so one can do this. Right? So far everything is good. And now what we are concluding is that you said that. Oopsie. So statement 2. So using 2. We know that there exists x such that x not equal to 0 such that ax is 0, correct? So what that means is that this side is 0, but this side is not 0. So that's not possible. Okay. All right, and then so theorem 13 was basically just saying that being invertible is equivalent to having let's say this is a invertible is equivalent to saying that ax equal to 0 has only trivial solution, has only all 0 solution, all 0x has solution. Right? So we just proved that Ax has to have all zero solution, right? That is the only solution that's possible if there existed a B that gives you B times A as identity. That's what we just showed. And so what that would mean is that using theorem 13, we conclude that A is invertible. Okay, and that's what the theorem was saying. The theorem was saying that if you have a square matrix, which either has, okay, so we were just doing the left part, so we were saying if it has a left inverse, then it has to be invertible. Right, so here, so the statement, this B, right, this is coming from the fact that you have a left inverse, and we concluded if you have a left inverse, then the only solution is the trivial solution. And the theorem told us that if you only have a trivial solution for a square matrix, it has to be invertible. Is that okay? Okay, brilliant. So now we're going to do the right inverse. For the right inverse, let's see how it's done. So let's start with saying that the right inverse is given by some matrix capital C. We're going to get capital A times capital C equals identity. So that's just by definition. And then capital C has a left inverse, that is capital A, right? These statements are fine, right? Because the definition of inverse is symmetry or whatever. Complementary, at least in this case, whatever. And so therefore, from our proof above, we can conclude that C itself has to be invertible. Okay? Because now C has a left inverse, and so therefore we can conclude C has an inverse. And so what that tells us is that we can write C inverse, it's a well-defined object, and if you multiply on both sides on the left by C inverse, then we get A equals C inverse. And then what does that tell us? That tells us that A itself is invertible using C. Okay? Is that clear? Alright. Yeah, so even though it says a corollary, it requires some work. I mean, so corollaries are normally supposed to be immediate consequences of theorems, but yeah. Okay, maybe immediate to the author, but it's not so obvious. Okay, so now let's move on. How much do we have left actually? Okay, we're doing good. We're doing good. I think we'll be able to finish this section. Okay. So suppose that you have a sequence of matrices A1 to AK, and they're all square matrices. Then the following statements are equivalent: that A is invertible, and each AJ is invertible. So one direction should be immediate, right? Like if all the individual matrices are invertible, right, then it should be the case that the whole thing is invertible, right? So one direction is easy. So let's do this, right? So if A1 to AK is capital A, and each A1 to EK is invertible, right? Then one can write, okay, so tell me what the inverse should be. Then A inverse is exactly. So AK inverse, AK minus 1 inverse, so on, A1 inverse. It's simply because we're going to multiply A inverse with A, right? So we'll multiply A inverse with A, right? And it will start cancelling things. Is that okay? And note that it works both ways, right? So whether you multiply it from the left hand side, so A inverse A, it will start cancelling from A1s, and if you multiply A with A inverse, it will start cancelling from AK inverse. Doesn't matter. Consistent. Right? Okay. So this direction is fine. So now let's do the non-trivial direction. So now suppose that capital A is given to be invertible. Okay. So we first show that A sub k itself has to be invertible. So A sub k is like the last one. Right? So let's see how to do this. And of course, we want to do it for each one of them, but the argument we'll see sort of one can apply repeatedly. So suppose that X is an n cross 1 matrix, and A sub k capital X equal to 0. Then we'll have AX, one can write as follows, right? So this is, we've just expanded, we've just used the definition. And now since capital A is invertible, the only solution to the system above is when X equal to 0. Right? This we just proved in this lecture, theorem 13. Okay? So since A is invertible, the only solution we're going to get is when x is zeros, and so therefore ak times x cannot have a non-trivial solution, right? Because if ak times x had a non-trivial solution, then this entire thing would have that as a solution, right? Because we just multiply. Okay. And now what that means is that because ak sub x cannot have any non-trivial solutions, again we can apply theorem 13. You see how powerful the theorem is, right? So now one can again apply theorem 13 and conclude that ak itself has to be invertible. Right? It's sort of this. Okay. Any questions? Is everything okay? Right? Okay. And now one can, instead of considering the matrix A being the same as A1 to AK, one can consider this matrix, let's call it A prime. And now it is essentially of the same form, except now you're just going up till AK minus 1. Right? And now one can just run the same argument again. Okay. There's nothing that stops us, because A prime is still invertible, right? It's a product of invertible matrices. It stays invertible. Okay, and then we run the argument again, and then proceeding similarly, you can show that for each aj, it has to be the case that aj is invertible. Is that okay? Okay, so that was lots of non-trivial statements. I hope that you guys are keeping up. It's not all that straightforward. But yeah, the notes are already actually online, so you can take a look. You can look at the test. Okay. All right. So let's continue. All right. So one final comment about the solution of linear equations is the following. So suppose that A is an m cross n matrix, and we wish to solve the system Ax equals y. Okay. Now, if R is row reduced echelon, which is equivalent to A, then R equals PA, where P is an invertible matrix. So we are using the corollary before theorem 13. Right? Because, so these are elementary row operations, right? And elementary row operations, we argue that they're invertible. Is that okay? Okay, so now the point is, so far we were discussing square matrices. Okay, so now we are looking at m cross n matrices. So that's the difference, like, just to highlight the fact. Okay, so now when we're looking at m cross n matrices, we are saying that you can always find a row reduced echelon matrix for an m cross n matrix, and so we're writing it as follows, and there would always be some p, right, that would correspond to the elementary row operations, and this p is going to be an invertible matrix, so we know that. Then the solutions for this system Ax equals y are exactly the same as the solutions for the system Rx equals Py equals Z, right? And that is because, so you have Ax equals y, right? And this P is an invertible matrix, right? So we can multiply both sides, and if you have an x satisfying the right hand side, it will also satisfy the left hand side. Okay? You can always multiply by P inverse and return to the previous equation, which will be true, because it's true for all x's, right? Okay. So this is fine, and then recall that PA is just capital R, right? So starting from this, these two will have the same set of solutions. PA we are going to substitute with capital R, and PY is the same over here, which we are going to call Z. So far it should be okay, right? Okay. And now, in practice, finding this matrix P is not much more difficult than finding the row reduced matrix capital R. So the procedure that we use to convert one matrix into its row reduced echelon form, what this is saying is that you can essentially use the same procedure to find solutions to non-homogeneous equations. Non-homogeneous equations meaning things like this one, right? Ax equals y. Okay, so it will give you like a recipe for doing this. And why that happens is because of the following. So what one can do is one can consider this matrix A prime, okay, and we call it the augmented matrix. So it's Ax equals y, and the augmented matrix is just, it's A and you put y as an additional column. It's like an added column. Okay, and this is what we're defining to be A prime. Okay, and now what we're going to do is we're going to perform on A prime the same sequence of row operations that was taking us from A to capital R. So what we do is we start with capital A. We want to solve Ax equals y. We construct this augmented matrix A prime. And now what we're going to do is whatever operations we were going to apply to take A to its row reduced echelon form, we're going to apply them directly to A prime. Okay, remember these are row operations, so it doesn't matter. If you add a few columns, you just apply the same operation also on those columns. Okay? Is it making sense? Okay. And then when we do this, matrix P will become evident. Okay, so let's go through an example quickly and hopefully make sense. So suppose the equation, so suppose capital A was this object, right? So it's this matrix. The augmented matrix is going to be this, right? So A prime is going to be this object. So this part is just A, and this part is what we're calling Y. So we just wrote it on explicitly. And now what we're going to do is we're going to apply the row reduced, the procedure to do row reduction. So we're going to multiply by 2 and remove it and so on. And in the end, you would end up with this final form, right? Where this is capital R. So this is row reduced echelon, and this part is okay. So this is the new part, right? Now it turns out that this matrix A, so this was from here we want to extract what we were calling P, right? So how we do this is basically we are just going to extract the coefficient. So we're going to find so we're going to find P is a matrix such that P times y1 by 2, okay, gives you exactly this matrix, whatever 1/7 y2 plus 3 y1 and 1/7 2 y2. So I mean the details are not important, but the point is that this is the matrix that we're writing. So when you write this matrix, yeah, okay, can someone tell me what this matrix should be? y1 y2, right? So we want this to be the first entry over here. So the coefficient of y1 is 3 by 7, right? The coefficient of y2 is 1 by 7, and then this one is minus 1 by 7, right? And then the last one is 2 by 7, right? And so you see this is exactly the matrix that they also have. Okay, so that's the matrix P. And the interesting thing is that this is actually A inverse. Okay, and this I will leave as an exercise. Okay, for you to convince yourself that it's actually giving you the inverse of the matrix. Okay. Yeah, I think this part you have to like sit and convince yourself. It's very hard for me to say it in words. Just go through these two examples. So go through example 15. So I'll leave this as homework for you, and go through example 16. And and then you should be able to convince yourself that indeed, if you follow this procedure, if the matrix A can be inverted, then A inverse would just be this matrix that you obtain using this procedure. Okay. All right. So we have 5 more minutes, so we can start the next chapter. All right. So what I will do in this chapter is basically I will start with giving you some intuition. Okay, so now we're going to start vectors. Okay, so we're going to look at vectors. So this part is going to be relatively straightforward. Is there any confusion? Is the proof is okay, right? The one that we saw. Okay. All right, so let's start with vectors. So what we're now going to do is basically we're going to generalize the notion of vectors. Okay, we're going to make it much more abstract. Okay, so let's consider the vector space R3, right? And this stuff you're already very familiar with, right? So we normally, when we are looking at Euclidean space, right, we ascribe 3 real numbers, right, to describe the location of a point. And from physics, we basically remember that if there are, there's a point P and there's a point Q, right? then a vector would usually be a directed line segment, right? That is, the length is the distance between P and Q, and then you have the direction that you're interested in. And so basically we are formalizing the notion of an arrow. And the point of a vector is that we only care about the length and the direction, right? So we want to say that any two line segments, right? Suppose this was P prime, Q prime. This also had the same length, okay, and the same direction. Then mathematically, we want these two objects to be the same. Right? We want to identify them to be the same object. And one way of doing it is to do the following. So you consider this line segment P and Q over here that I had drawn, right? So suppose that P was at x1, x2, x3, and Q was at, say, y1, y2, y3. Okay. And now instead we consider vectors that are starting from the origin. So 0, 0, 0, okay, and now it's going to y1, or basically it's going to shift, right? So it's going from y1 minus x1, y2 minus x2, y3 minus x3. Right? So is it time? I have 3 minutes. There's 3 more minutes, you guys. Almost done. Okay. So these two vectors, right? We want to associate them, right? We want to identify them to be the same vectors, right? So what we are therefore going to do is we are basically just going to restrict to. So we're going to describe vectors instead of looking at 2 points and then talking about the difference. We're just going to look at R3, for instance. Right? So it's understood that the first point is at the origin. Sort of. That is the basic idea. Okay. And in the definition of our vector space, we're just going to, okay, this is what I just said. And okay, and then there are going to be 2 sorts of operations that we're going to add. So we'll formalize it in the next class, but intuitively we look at 2 operations. Right? So one operation is how do you add 2 different vectors? Right? So this you've seen in physics like a million times, probably by now. But it's just the parallelogram rule, right? Like, so you have this object, and you create this parallelogram, and then the coordinates of this final vector are going to be the definition of addition of vectors. Right? Is that okay? So this is fine. And what about scalar multiplication? Well, you basically replace the length by c times the original length, right? And you flip the head of the arrow if c is negative. That's it. So why I'm telling you all of this is because we can now try to abstract out the important properties of such objects and then study them at a more abstract level. And the advantage is that this will apply to many more interesting objects. Like, for example, you can take polynomials as vectors. You can treat complex numbers over reals as vectors. And so these are very general. Like, you can take combinations of differential equations, linear equations. Right? All of these things end up forming vector spaces. So what we're going to do is we're going to systematically formalize what it means to be, what a vector space means, describe these 2 operations, and then using this, we are going to, write theorems and things and try to figure out what are the general properties. The point is that we want to be lazy. We don't want to prove the same results for all the different kinds of objects. We just want to abstract the key properties, and using those properties prove results that are applicable to a very large class of objects that are of interest. So here in particular for physics, but also for other disciplines. Okay? So that's the motivation. So we will start next time. Thanks.
The set of real numbers we consider a trivial subfield of complex numbers.
Set of real numbers is a subfield of complex numbers.
But would we consider a trivial subfield is what I'm asking.
Oh, trivial would be complex itself, right? That would be trivial.
Trivial would be complex itself and the empty set, right?
Yeah, empty set, these things are completely trivial. So you can use reals, you could use rationals, things like that.